In this video, we'll solve this problem. We'll find bases for all eigenspace of the linear transformation that sends the matrix A to A plus the transpose of A. So the way we'll do this is we'll find a matrix representing T, then we'll find the eigenvalues and eigenbases of that matrix, and we'll translate them back into M22. Alright, so I'm going to use, there's no need to be fancy here, I'm going to use the standard bases. So let me give these names to make our lives easier. Let's call this A1, A2, A3, and A4. To find the matrix of T in this base, I'll need to find where each of these bases matrices are sent. Then write that as a linear combination of these. So let's start. If I take T1, T of A1, that's A1 plus A1 transpose. A1 is 1, 0, 0, 0. If I flip it, I get exactly the same matrix. So I get 2, 0, 0, 0. Let's rewrite that in terms of a basis. That's twice A1 and that's it. So that's 2 times A1. If I do the same thing for A2, I'm going to take this and its transpose and add them. So 0, 1, 0, 0 plus 0, 0, 1, 0. I get 0, 1, 1, 0. This time I get A2 plus A3. If I do the same thing for A3, I'm going to get A3 plus its transpose. Same matrix as here, so A2 plus A3 again. The final one, so A4 plus its transpose, that's going to give you 0, 0, 0, 2. That's twice A4. And so I'm ready to write the matrix of T with this basis. So T, B, S. Each of these computations will give me one column. For the first column, I have to look here. It's twice A1. So I'm going to get 2, 0, 0, 0. For the second one, it's A2 plus A3. So 0, 1, 1, 0. Same thing for T of A3. T of A4 is this. Alright, so that's the first step. Finding a matrix that represents T in any basis. I chose a simple one just to make my life easier. Alright, second step, find eigenvalues and eigenbases for this. So here's the determinant I need to compute. I've already done it. and I got x times x minus 2 cubed. That means I have two eigenvalues. I get lambda equals 0 and lambda equals 2. So I have my two eigenvalues, 0 and 2. Those will turn out to be eigenvalues for the linear transformation t as well. For now, let's find eigenvectors for these. Let's start with lambda equals 0. TBS minus 0I. That's going to be just that matrix. And if I reduce it, you'll get 1, 0, 0, 0, 0, 1, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0. And I have one free variable. I have a free variable right here. So I'm going to get one eigenvector for the basis. I'm going to get 0, minus 1, 1, 0, s. So the basis will be just that vector that multiplies s. Now this is not a basis for t, it's a basis for the matrix here because I'm expecting to get matrices out of this. Alright, let's do the second one. If I take lambda equals 2, what I'll get I get this, which reduces to this matrix. Now I'm going to have a free variable here, a free variable here, a free variable here. So I'm getting a three-dimensional subspace on that side for that eigenvalue. And so in this case, A, B, C, D will be 1, 0, 0, 0 times T plus 0, 1, 1, 0, S plus 0, 0, 0, 1, U. So my basis for lambda equals 2. Will be this. And now we're ready to get back to the basis for t itself, not for the matrix representing t. So in M2 cross 2 for lambda equals 0, you'll get one matrix, you'll get 0, minus 1, 1, 0. And for lambda equals 2, you'll need 3. You'll get 1, 0, 0, 0, 0, 1, 1, 0, 0, 0, 0, 1. All right, just for fun, let's check. Let's take this one. I want to check that it's an eigenvector, so I'm going to apply t to it. I'll get a plus at. So I'm going to get 0, minus 1, 1, 0, plus the transpose. And so that's going to give me 0, 0, 0, 0, which is indeed 0 times A. So this matrix is an eigenvector for the linear transformation with eigenvalue lambda equals 0.